Welcome to Fundamentals of Gas Chromatography Training. In this module, we will explore the theory of GC columns and separation. By completing this module, you should be able to identify a packed versus capillary GC column, describe the unique features and differences of a packed versus a capillary GC column, describe how peak separation occurs in a GC column, apply the concept of theoretical plates and the Van Deemter curves to the GC method setup, select the appropriate carrier gas for a GC analysis, select the correct column for a GC analysis based on its dimensions and stationary phase. There are two primary types of columns used in gas chromatography: traditional packed columns shown on the left and open tubular capillary columns on the right. Packed columns are either glass or stainless steel tubes filled with a dry, inert solid support such as diatomaceous earth. The liquid stationary phase is coated onto this solid support. Capillary columns are small diameter open tubes with a thin coating of stationary phase on the inside wall. Capillary columns have much less sample capacity than packed columns. This means that relatively concentrated samples will either have to be diluted before injection or split inside the GC inlet. Most applications today use capillary-type columns. However, there are some specific applications, for example, fixed gas analysis, where packed columns are still used. We'll cover more about packed columns later. Capillary columns are made out of fused silica glass, which is drawn to a narrow ID tube in very long lengths. Fused silica is a pure form of glass that is very inert and exhibits almost no interaction with the sample components. Uncoated fused silica is very fragile, so it is coated at the factory with a high-temperature polymer called polyamide. This results in a flexible piece of tubing with greater mechanical strength and flexibility. The inside layer of the capillary column is the stationary phase. This is where the GC sample separation occurs. Capillary columns are available in various sizes. The key dimensions and features are shown here. Internal column diameters are commonly 100 up to 530 microns. Column lengths can be 5 to 100 meters or even longer. This area is the liquid or stationary phase. This is where the chemistry occurs inside the column. The amount of stationary phase is indicated by the film thickness, which can be anywhere from 0.5 to 5 microns. While we are talking about the stationary phase, it is good to remember that significant damage can be done to the column if it is heated above 70 degrees centigrade with even trace amounts of oxygen in the column. For this reason, always purge the column with carrier gas before heating. Use carrier gas that meets the 99.9995% purity specification, install moisture and oxygen traps, and check for leaks inside and outside the GC routinely. Also, it is important to understand that the stationary phase of each column has a unique maximum temperature. Taking the GC oven to a higher temperature may result in column damage. Here is a partial table of the numerous capillary column stationary phases and their associated applications. Notice that like dissolves like. Polar wax type columns are used to separate polar samples, like alcohol, and nonpolar columns are used for hydrocarbon analysis. The GC column is where sample separation takes place in the stationary phase. The stationary phase is usually a very high molecular weight liquid. It is very viscous, almost a solid at room temperature. The sample is injected into the GC injection port and vaporized at a high temperature. It is then carried through the column by the carrier gas, which is also called the mobile phase. The flow rate of the carrier gas is very accurately controlled by the pressure in the injection port. While the sample is swept through the column, it goes through a series of interactions where it is absorbed into the stationary phase and then desorbed back into the carrier stream. Each of these interactions is called a theoretical plate. Each sample component is retained based on its solubility in the stationary phase and the boiling point of the sample component. To maximize sample separation and minimize analysis time, the GC oven is usually programmed from a low to high temperature after the sample is injected. Thick films are good for very volatile compounds. These compounds are difficult to retain on the column without going to very low column oven temperatures. With very thick film, 5.0 microns, you can separate methane, ethane, propane, and butane at room temperature. Thick films are often employed in headspace applications due to the high volatility of the analytes. Thick films can also aid in increasing the sample capacity of the column. If you need to inject a more concentrated sample, you may consider a thicker film. Thicker films are otherwise undesirable because they lead to lower column efficiencies and tend to bleed more. Column bleed usually results in a rising detector baseline during the oven temperature program and can introduce background noise and interference into the detector, decreasing signal to noise. Thin film columns are generally preferable for most applications. They yield higher efficiencies and faster analysis. With thin film columns, it is important not to overload the column or fronting peaks, as the one shown here will result. A good guideline is to keep the amount of sample per peak under 10 nanograms. This makes capillary chromatography ideal for splitless mode trace analysis, like pesticide residues or drug metabolism studies. If peaks are fronting, you can inject less, operate in split mode, dilute the sample, or choose a thicker film column. The Van Deemter plot relates carrier gas linear velocity or flow rate to the column efficiency. From the plot, one can determine what column flow rate or linear velocity to use for an analysis to yield the most efficient peaks. Van Deemter originally plotted this as the height equivalent to a theoretical plate called HETP versus average linear velocity. HETP is defined as the length of the column divided by the number of theoretical plates. From this plot, the minimum area of the curve, shown in red, indicates the average linear velocity or flow that will result in the sharpest and most well-resolved peaks, resulting in the best column efficiency. In the Van Deemter equation, A is the eddy diffusion term. This only applies to packed columns because of the random sample flow path that doesn't exist in a capillary column. B is the longitudinal or ordinary molecular diffusion term. This is observed in the tendency for sample peaks to broaden at low flow rates while in the column. C is the resistance to mass transfer term. This results from pushing a peak through the column at higher flows or using thicker films, limiting sample interaction with the stationary phase. Type of carrier gas. The type of carrier gas used has a significant effect on column efficiency. From the Van Deemter plot, you can observe that when nitrogen carrier is used, best efficiency is achieved at very low average linear velocity. Using hydrogen allows for the use of faster column flow, resulting in shorter analysis times. Average linear velocity is defined as the column length in centimeters divided by the retention time in seconds of an unretained peak like air or methane. Optimum linear velocity for helium carrier is about 20 to 30 centimeters per second. For a 320 micron column, this translates into a column flow of about 1.5 milliliters per minute. From the second diagram, you can see if nitrogen is used at the fast linear velocity of 58 centimeters per second, resolution of the two peaks is lost. Here is an example of a thin film column yielding very high resolution. How many compounds are in a hydrocarbon refining stream? The answer is a lot. One of the separations routinely done in the hydrocarbon processing industry is a detailed hydrocarbon analysis. In order to achieve the desired separation of hydrocarbon isomers, a narrow bore, 100 meters long column is used. Under isothermal conditions, this column can generate almost 500,000 theoretical plates. The analysis takes almost 3 hours to complete, but resolves nearly 1,000 compounds. The magnified region shows that baseline resolution is maintained for these test components. When necessary, GC can provide extremely high resolution. Packed columns are literally packed with a material for adsorption or absorption of the sample components. This is usually an inert, solid support like diatomaceous earth that is deactivated, then coated with the stationary phase. Packed columns are typically made of stainless steel or borosilicate glass. Packed columns are much larger in diameter, typically 2 or 4 millimeters. Packed columns are usually 0.5 to 10 meters long. Packed columns require much higher carrier flow rates than capillary columns in the range of 20 to 60 milliliters per minute. There are some specific applications, especially separation of fixed gases, where packed columns are still used. Packed columns for separating gases come in two main varieties. A molecular sieve is a material containing tiny pores of a precise and uniform size that is used as an adsorbent for gases. Used in GC, the MulSieve column will separate light fixed gases while adsorbing water, carbon dioxide, and heavier hydrocarbons. HACIP or Poropack columns are comprised mainly of porous polymers and are used to separate very light hydrocarbons. Neither the MulSieve or porous polymer columns have a liquid phase. These types of columns are also available as capillary columns known as plot, or porous layer open tubular columns. The chromatogram shown is a fixed gas separation on a MulSieve column. The chromatograms shown here compare the same sample separation on 3 different columns. The first chromatogram is the result of using a packed column. The next 2 chromatograms are with progressively narrower diameter capillary columns. Note the packed column peaks are broad and poorly resolved. The 530 micron column peaks are sharper, with about the same analysis time and much better separation. On the 320 micron column, the peaks are even sharper, and now all the compounds are completely resolved. In conclusion, the analyst can achieve better resolution, that is, separation, and better efficiency or sharper peaks as the column diameter becomes narrower. This is a table summarizing typical lengths, internal diameters, pressure, and flow rates, and sample capacities for packed and capillary columns. Hopefully, this table and the information provided to you in this training module will be helpful to you as a gas chromatographer. Visit the Agilent GC Column Selections website for specific column information.